Okay, this video is for AP Calculus, and we're going to wrap up the rest of the computing derivative unit here with some odds and ends about computing derivatives. We're going to talk about trig functions, derivatives of inverses, and higher order derivatives here. So first of all, we've already seen that the derivative of sine is cosine and the derivative of cosine is negative sine, but there are four additional trig functions. So we want to go ahead and talk about what those derivatives are. We will have to memorize these. There's proofs here. I'm going to scan through here really quickly and show you the proofs. You can pause the video and read through each part if you like, but let's take a look at if the function was tangent of x, what would be the derivative of that? Well, the tangent can be rewritten as sine over cosine, which means we can use quotient rule for the derivative. And if you simplify, you end up computing that it's 1 over cosine quantity squared, which is, since 1 over cosine is secant, it's secant squared. So we'll need to memorize that the derivative of tangent is secant squared. The derivative of cotangent, similarly, I'll show you the proof here, first half, second half. The derivative of cotangent is negative cosecant squared. And it turns out that the derivative of secant, here's the proof of that. Since secant can be replaced with 1 over cosine, again, we can do quotient rule. And we end up getting that the derivative of secant is secant times tangent. Similarly, for cosecant, here's the proof of that derivative. It turns out that the derivative of cosecant is negative cosecant times cotangent of x. And then there are also inverse trig functions, so arc sine or inverse sine, arc cosine, arc tangent, and so on. Let me show you one example of this. I thought it was interesting enough to actually look at how this is derived. How is it that we figured this out? Well, if we want to figure out the derivative of arc sine, we can define y equals arc sine of x. Let's say, so x is the input. And that means if you were to take the sine of both sides, the left side would become the sine of y, and the sine and the arc sine would cancel and give you x. So if y is arc sine of x, then sine of y equals x. What you can do is you can connect that with a triangle. This y is behaving as if it was an angle. So if I put this in an angle in a right triangle, and that means the sine would have to be x over 1, and that is the opposite side over the hypotenuse. So we can make the opposite side the x and the hypotenuse 1. And then that means that we can do the Pythagorean theorem to find that this last remaining leg is the square root of 1 squared minus x squared, or the square root of 1 minus x. Right, so it gives us a way to relate the sine to this kind of structure with a triangle. Then we can take this equation here and do implicit differentiation. So the derivative of sine is just cosine of y, but then by the chain rule, times the derivative dy dx, because that is not an x. And the derivative of the x is 1, which means that dy dx is 1 over cosine. Okay, but this cosine, we can go back to this triangle and say cosine of the angle is the adjacent side over the hypotenuse. Therefore, it is the square root of 1 minus x squared over 1. So I can replace this with that, and that means that this derivative of y is 1 over the square root of 1 minus x. Therefore, the derivative of the arc sine or inverse sine of x is 1 over the square root of 1 minus x squared. Okay? And this arc sine can also be written this way, with a little 1 as if it was to the negative 1 power. That's an exception to the rule. When you have something normally, like if you have x to the negative 1, that means 1 over x, right? But if you have a function raised to something like that, then that's interpreted as meaning the inverse of that function. So the inverse of sine can also be called arc sine, or the angle whose sine is x. All right, so the derivative of arc sine is 1 over the square root of 1 minus x. And we're going to add that to our list to memorize. In fact, let's make a list of everything we should have memorized. The derivative of cosine is 0. The derivative of x to a power is n, x to the n minus 1, the power rule. The derivative of e to the x is a copy. The derivative of a to the x is a copy times the natural log of a. The derivative of log is 1 over x. The derivative of log with some other base is 1 over x divided by the natural log of the base. Derivative of sine is cosine. Derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is secant times tangent. Cosecant is negative cosecant times cotangent. And cotangent is negative cosecant squared. We now just showed that the derivative of inverse sine is 1 over the square root of 1 minus x squared. And the derivative of tangent can be shown to be 1 over 1 plus x squared. And then there's these other 4 trig functions, arc secant, arc cosine, arc cotangent, arc cosecant, right? And they have inverse derivatives as well. These 4 are rarely used in the course and also on the AP exam, but these 2 are frequently used. So we say you should definitely add these to the list to memorize along with all the 6 normal trig functions and all the other function families so far. Right? So all of this, except you can omit this, but all the rest of this you need to memorize. Okay? As well as the other rules, like the fact that the constant can come out of the derivative. You can do terms that are separated with pluses and minuses separately and just recombine the derivatives. But when it comes to products and quotients, you have to use the product of quotient rule, and we also have the chain rule. And you should also know simple trig things like the fact that the secant of an angle is 1 over cosine, right? The quotient identities. You should know tangent is sine over cosine, and you should also know what we call the Pythagorean identity. Sine squared of x plus cosine squared of x is equal to 1. Right. Next topic, besides adding on to the list for trig functions, is that you can take a derivative of a function, and that produces a new function, which means you could take a derivative of that function, and that is therefore called a second derivative. So I'll give you an example. Let's say that we had y equals x to the 8th plus x to the 5th. Okay? The first derivative would be 8x to the 7th plus 5x to the 4th. But that itself is a function, so you can take a derivative again using the same rules. This would be 56x to the 6th plus 20x cubed. And so what do we label that? It's the derivative of the derivative. It's called the second derivative, and we just add another prime. So that's called y double prime, the second derivative. So if you have a y, you just add dots. Same thing for a function notation like f or g double prime. If you want to show a derivative operator, the d dx becomes d squared dx squared. It means to take the second derivative of this function. Right? Or you can write it this way. The result is dy dx. This is written d squared y dx squared. Why is the square here instead of here? Because if you imagine that you're taking, I'll use y. If I took the derivative operator and applied it to y, the result of that would be dy dx, because this just moves to the top of the fraction since it's a multiplier. But then if I take the derivative again of that, you can kind of see why this is d squared of that y, and then there's 2 dx's being multiplied together. And so the standard notation for that is d squared y dx squared. It's another way to say f double prime or y double prime. Right? And then you can take another derivative, and that would be called the third derivative, which is y triple prime, or a 3 here. Once we get past that, though, we don't try to keep putting more and more little tick marks because it gets hard to count them. So we use the prime notation up until the third derivative, and then the next derivative is labeled the fourth derivative, and you put the number 4 but in parentheses, y raised to the 4th power. What it really means is if that's in parentheses, it means the 4th derivative of y, or f to the 4th, right? And that can be extended to any number. Okay, so that's called a higher order derivative. We will see that more later when we get to applications. There's another theorem that is covered in the textbook. It's not frequently encountered, but occasionally you do see this on a multiple choice question on the AP exam. It's if you have two functions that are inverses of each other, they undo each other, then it turns out that the derivative of one of the functions is 1 over the derivative of the other function with the non-derivative of the other function of this function plugged in. This can be derived with the chain rule. So let me actually show you what I mean. What does it mean to say these functions are inverses? So for example, let's say f of x is x squared and g of x is the square root of x, right? That means that if I had f of g of x, That means we would be taking the square root of x and putting it in a square function. And since the square and the square root cancel each other out, that will just leave the x. So any function that is defined as an inverse has that property that f of g of x just uncovers the original x. So since that's true, you can use the chain rule to take the derivative. So the derivative on the left side is the derivative of the outer function f prime with g plugged in, but by the chain rule times the derivative g prime of x. And the derivative of x over here is just 1. That means that if you solve for this by dividing by this, g prime of x is 1 over f prime of g of x. I mean, it's a fairly esoteric theorem, but here's an example of a multiple choice question from an AP test where they are asking something where you would use this. If f of x is x cubed plus x, and g of x is the inverse of f of x, and g of 2 is 1, what is the value of g prime of 2? All right, so I'm just thinking on the side, if I encountered this, and as soon as I see inverse, that's an inverse, then I'm thinking, okay, that means that f of g of x undo each other so that we get x. So the derivative over here would be, if I take the derivative of f of g of x, then that would be the outer derivative with the inside plugged in by the chain rule times the derivative of the inside. And this would be a 1. And so that means that g prime of x is just equal to 1 over f prime of g of x, which is what that theorem says. So what that means is that g prime of 2 is going to equal 1 over f prime of g of 2. And since they told me that g of 2 is 1, that means I'm going to replace this with a 1 here. Then I have to find a way to plug x equals 1 into the first derivative of f. They gave me f, which means that if I know f is equal to x cubed plus x, I could take the derivative, 3x squared plus 1, and evaluate that at 1 by plugging a 1 in here and getting a 4. So this actually would be 1/4 is the answer here. Right, so a fairly esoteric problem, but that's how you would solve that. You would need this extension of the chain rule for a derivative of inverses. Okay, let's just look at a couple other things involving trig. Here's a function, f of x is sine x over 1 plus cosine x. And we want to find the first and second derivatives. All right, so the first derivative, f prime of x, that looks to me to be a quotient structure. So I'm just going to do quotient rule. It's low function, 1 plus cosine of x, times the derivative of high. Derivative of sine is cosine. Low d high minus high, derivative of low. The derivative of a constant is 0. And then the derivative of cosine is negative sine over low squared. Okay, let's simplify that a little bit. We have, I think I'm actually going to multiply this out. If I were to distribute this, I would have cosine of x times 1 plus cosine of x times cosine of x, which is the cosine squared. And I have minus minus, so that's plus a sine times a sine. Okay, and that's over 1 plus cosine x squared. The reason I'm simplifying that is because it turns out that cosine squared plus sine squared is actually equal to 1. And so that means that this can be further simplified to cosine of x plus 1 over 1 plus cosine of x squared. And since 1 plus cosine of x is the same as cosine of x plus 1, that just means we have the same structure on the top. We just have one of them there and two of them there, so one of these can cancel one of these off, and you're just left with 1 over 1 plus cosine of x. So after all that, we've got 1 over 1 plus cosine of x, right? Is it 1? Let's see, yes. Yeah, that's right. Looks like my notes actually are wrong. I'm going to have to change that. All right, so this is 1 over 1 plus cosine of x. Now, I'm going to change colors, and let's do the second derivative. So the second derivative would be marked f double prime of x. Really important to label things here so that the scorer can tell when have you switched to now working on the second derivative. I'm just going to use quotient rule for this over again. So that is low, which is 1 plus cosine of x, d high, that's a constant, so the derivative is 0, minus high times the derivative of low, that is 0, minus sine, because the derivative of cosine is negative sine, over low squared. And then we could just leave that like that, or we can simplify this. So this whole thing is a 0 here, and this is just a negative negative, so that is a positive sine x over 1 plus cosine of x squared. Okay, so now we have the first derivative, and we have the second derivative. So that was mainly showing that this notation means the second derivative. Let's do another one. Find the equation of the tangent line to the curve. Okay, so I'm just thinking the goal here is to produce a tangent line. So I'm thinking we got y minus y0 equals the slope times x minus x0. And the point is 0, 1, so that's going to be y minus 1 equals some slope times x minus 0. For this, we're going to plug in f prime at the point 0, 1. Okay, so we'll evaluate f prime at x is 0. All right, so that means we'll have to take the derivative. So the first derivative here, y prime, or f prime of x, is 1. The derivative of cosine is negative sine. And so f prime at 0 is 1 minus sine of 0. And on a unit circle, the angle 0 is over here, where we have 1 comma 0. The sine is the y, so it is 0. That is 1 minus 0 or 1. And that means this is the slope. We're going to plug a 1 in for that slope. So you just leave it in point slope form whenever you're asked to find a tangent line. Okay, and you can always pause any of these, like pause this and give this a try. We're trying to find y prime from y. Okay, so I would just go ahead and say y prime. The derivative of this term, so I'm just noticing there's a negative sign here that separates us into two terms, and each of them we can do separately. So the derivative of this term is 1 over the input, which is t squared plus 4, times the derivative of the inside, which is 2t, since the variable is t. And we have minus, there's a constant 1/2, and then I have the derivative of our tangent, which it turns out is, let's just note what that is. We're going to memorize that the derivative of arctangent, I'll use t here. The derivative of arctangent of t would be 1 over 1 plus t squared. And that comes from the sheet that we're memorizing. And here it is here. Arctangent is 1 over 1 plus x squared. All right, so then that means in this context, we're taking the, this is going to be 1 over 1 plus, but then I really have a t over 2 there, squared. And that means that that derivative, that's a function, that's not just the t. So if we did have y equals 1/2 t, then the derivative of that would be just 1/2. So by the chain rule, we have to multiply by another 1/2. So this is the answer here. That's a t right there. So we used our new arctangent shortcut there. Right, and that is the last example for this. There's many, many different ones that we can ask here. The main thing to take away is it is imperative that you memorize everything other than these 4. You can memorize the rarely used ones, but all of these other ones must be memorized. And the quicker you memorize them, the easier the course will get.